So I will try to compensate, absence of philosophy in Eric's talk because he was showing too many formulas. In my talk, at least first talk, there will be practically no formulas at all because it's based on public talk, which I was delivering in relation with 100 years of general relativity. And I think I was the first guy in this universe who gave talk in 2015 because it was 1st of January at 9:30 in the morning in Jerusalem, winter school, you see. But let me start not with universe, but with some kind of general principles, because here I put quote. I never understand why the theory of relativity with its concept and problems so far removed from practical life should for so long have met with a lively or indeed passionate resonance among broad circles of the public. I have never yet heard a truly convincing answer to this question. How do you think who could write it? No guesses, who could say this thing? Only Einstein, but not earlier Einstein, but late Einstein. He said this thing in 1943, and he repeated the same thing practically word by word in 1953. In 1920, when he was asked if observation would not confirm your theory, what would be your reaction? Then he said to the journalist, I would be sorry for Lord. You see, but you understand that with time people are evolving, sometimes become more reasonable, in many cases less reasonable. Einstein was a very reasonable guy, as you know, perhaps, but in fact, there was no real experimental confirmation for his theory. Because if I ask you, why do you believe in general relativity? I asked this question some guy from Princeton, who's my main cosmologist there. Then he was a little bit in trouble. I told him, because you learned it like in the school, like Bible, and this is the reason why you believe in it. And for instance, Brillouin, some experimental physicist, wrote some secret notes which he never published, but his student published it. It was critical notes about general relativity, where he called general relativity that it's a giant which is standing on the sand legs, you see, and can collapse at any moment of time. So, of course, for any physical theory, there should be experimental confirmation. So what are experimental confirmation were at the time of Einstein? Tell me two. Because the third one, redshift, in the constant gravitational field is what it was not yet done, because it was done after discovery by Mersbauer effect. So it was done by Pound and Repka in 1960, I guess, something like this, or maybe 59. But there was, of course, advance of perihel, but it was not prediction, it was postdiction, because for the perihel of mercurium, the whole advance of the perihel was about 540 something seconds, and only 40 arc seconds per 100 years, yeah. Only 42 were not explained by the perturbation from the other planets. So the easiest way would be to postulate little modification of the Newtonian law, or to assume that there is extraplanet instead of building this kind of huge theory. And at the beginning, of course, Einstein was saying that he wanted to realize Mach principle, but in 5 years he said, forget about Mach, I have nothing to do with this guy. You see, and what came out, then came out. Then, what was the other confirmation?
Solar eclipse.
Bending of light. in fact, I was teaching general relativity for many years and was always quoting the same numbers. Okay, because there was two expeditions. One was in Brazil and the other was some small island, I forgot how it's called, in Africa. In Africa was very bad weather, first of all. So they got just 5 images of the stars, which they could use. In Brazil, it was better, a little bit, but much better. So they got 16 images. Why they needed so many images? Because fluctuations in the atmosphere do not allow you to get better resolution than 1.5 seconds. You see? And adaptive optics at this time, of course, was not known. There was no computer. Therefore, you have to have a lot of images to make averaging. It was the first thing, but nevertheless, Eddington applied in 1917 for grant to have these kind of 2 expeditions, in spite of the fact that he was going to verify the theory of the guy from the country with which England was fighting. And he got this grant. It was £1,000 only. You see, for 2. So now you can see what was the inflation, yeah? £1,000 for 2 expeditions. Now, then the result was published, and then, of course, it immediately attracted the attention of all the journalists. And Einstein was writing to his mother, one day I woke up and I became famous. Nobody before knew about me. And even after that, when Einstein was going to second survey, he didn't get any visa. Why? Because, okay, people confused him with a famous spy with the same name Einstein. And Lawrence was writing that our Einstein has nothing to do with your famous Einstein. Our Einstein is a little Jew with little Jewish wife. You see? It's not a joke, actually. It's historical fact. But it was already 1930. Now, when I was teaching general relativity, I was always quoting 1.71 plus minus 0.3 arc second. And the other one was like 1.9 plus minus 0.1. And I could never understand what does it mean, this plus minus something, because you understand that you never know. Is it systematic, statistic, or whatsoever? Then I searched Wikipedia, and I never found the big improvement of this kind of measurement of the bending of light since then. And there is nice review by Cliff Weil, who reanalyzed the whole thing. Of course, it's not the best thing, okay, to be measured and solved. And the first prediction of the bending of light, as you know, was in optics by Newton. But it was twice less. After Newton, who was the second guy who predicted the bending of light? Cavendish. 1800, yeah? 1018. Then after him, a year later, was von Soldern. This was the reason why some German who hated Einstein was telling that Einstein was blaming him in plagiarism, okay? And also 0.3 is not so convincing even if you understand it as, for instance, 1 sigma. But then people also reanalyzed the photoplates obtained in Brazil by von Soldern, and then they discovered, of course everything could happen during so long time on photoplates, that his result was 1.5 plus minus 0.4 instead of 1.9 plus minus 0.1. Therefore, it was not quite clear. Second thing, in 1936, Einstein wrote paper where he wrote that there is no gravitational wave at all. Why? Because together with Rosen, they managed to get exact solution, what is called PP waves. And this solution, when you look at it, has singularity. Therefore, Einstein abandoned the existence of gravitational waves. He sent the paper to physref D, and he got referee report by Robertson, whom you mentioned, who wrote that, guys, look, it's just simply coordinate singularity. Therefore, you can forget about it. But Einstein was furious, and he wrote to physics, physref D, I am sending my papers for publication, but not to be refereed. And he never, ever after that published this paper. You see? Therefore, you understand that actually he was a little bit frustrated. Today, of course, everything is confirmed, but thanks to cosmology, in spite of the fact that, for instance, in 1980, when I came in cosmology, all particle physicists were laughing on cosmology. Then, 30 years later, all cosmologists were laughing on particle physics. Because at a certain point, okay, with the last experiment, okay, nobody cares about it. Moreover, as you know now, there are so-called fantastic fundamental theories, and everything should follow from this theories. And I asked, but who decides what is fundamental theory? And then some philosopher, the friend of Eric, wrote a book where he wrote the string theories in particular used as a method of non-empirical theory confirmation. This method is used during the development of a theory and is based on collecting indications which increase the physicist's confidence that the theory, a theory describes nature. You see, these indications are, for example, the amount or absence of alternative solution of a problem, the degree by which a theory is connected to already confirmed theories, and the amount of unexpected insights that the theories give rise to. Now, first of all, the word a theory is nonsense. And if you look, there is actually a very good movie on YouTube when Feynman for 10 minutes was making joke from a theory. Because, look, I, as a Russian, I have troubles with the articles, but in this particular case, I know that you have to use the theory if you really pretend on anything. And the problems, but not a problems, you see? And in fact, actually, this kind of attitude, of course, contradicts to the smart people who were writing about philosophy of physics in past. You know, the two best historical books, one about French Revolution and the other about Roman Empire, by accident were written by English people, as you know very well, because the best ever written book in the history is the book by Gibbon, The Fall and Decline of Roman Empire. The only disadvantage of this book is that it's too short, 3,500 pages. And in distinction from other historical books, it's not boring. Therefore, all historians are very unhappy about these nice stories which Gibbons was writing during 20 years. Okay, I recommend it very highly, but why I mention him? Because in his book, he wrote that the physics, both of the academy and the lyceum, they are built not on observation, but on argument, had retarded the progress of real knowledge. I think it's a very good remark because I recall what Platon was writing to his friend. He told, okay, come on, you will not be happy if your daughter will marry engineer. So they were treating all the practical professions like low-class professions, you see. On the other hand, also, Galileo Galilei, who was, by the way, I think, rehabilitated by Catholic Church not so long ago. And you know, by the way, when Catholic Church finally admitted that the Earth is not in the center of the universe. Do you know when? In 1820, after Napoleon. And Galileo, okay, got complete rehabilitation. I don't know when it was 1982 perhaps, or something like this one. Even I think Stalin victims were rehabilitated much faster. You see, and here it required 200 years. So Galileo wrote that in questions of science, the authority of thousands is not worth the humble reasoning of a single individual. The modern observations deprive all former writers of any authorities. Therefore, cosmology, which, by the way, is the final confirmation of general relativity, plus quantum mechanics, but quantum mechanics actually is confirmed in thousands of the experiments. We didn't need to make this kind of delayed choice experiment because it was confirmed before 1,000 times, you see? I just don't understand why people make so much noise out of it, yeah? So, therefore, now I go to the main topic of my talk, the quantum universe. It will be about our universe. But let me go to prehistorical times, because you understand that, okay, of course, when I was writing papers, I was not thinking about making great contribution in science. I just wanted to defend my PhD. It was the only reason. When I asked Jacob Bekenstein how he managed to come to this entropy of the black hole, he told, oh, you come to either blah, 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 you come out, you have nothing in your hand with what you can start calculation. And I wanted to defend my PhD. This is the reason why, okay, I wrote about entropy of black holes. Good paper, okay? At the beginning, Hawking was strongly against it because Hawking's main argument was that if Bekenstein is right, then black hole should emit radiation, which he himself discovered in a year after that, you see? Okay, it's actually interesting story, but let me go to the history of the universe, okay? Weinberg, who was a very practical guy, in his book, The First 3 Minutes, wrote the thing which, by the way, completely literally repeats what Tolman has written in his book on cosmology, thermodynamics, and gravitation. The efforts to understand the universe is one of the very few things that lifts human life a little above the level of farce. I like in this sentence, a little. You see? Now, here is the summary of my talk. You see? On the first, and both pictures is not Hollywood, is not actually painting by Raphael or by whom you want. It's 2 real pictures. Left is the hydrogen atom in the ground state, and right is the picture how universe looked like, photograph, when it was 300,000 years old. Just 300,000 years old, you can call it young universe, because today it's 13 billion years. And what these 2 pictures have to do with each other? One refers to the scales which are today megaparsec scale, and the other refers to the atomic scale. Behind both of these pictures, there is the same formula, which is called Heisenberg uncertainty relation. Somebody told me a very, very funny story, yeah? Because he studied also in this Physical Technical Institute, and there was some guy who was, I think, in parallel working in KGB also, but this guy knew nothing. And then when he came to the exams in quantum mechanics, the only formula which he knew was this formula. Because he has read book by Marx, but not Karl Marx, but the other Marx from Hungary, yeah? And in his book, he had only this formula. in the popular book. Then professors didn't know what kind of grades they have to give him, because even two lowest one was too much. Therefore, they decided to give him the highest grade 5. It's a real story, you see. And the guy was very proud that he didn't know anything. But nevertheless, it's important formula, which really cost 5 or even more. Now, let me now go to the history before 1990, because cosmology started to be natural science only in 1990. As I recall that when I moved to Germany, we had some neighbors, and their friend was some Jesuit priest. And he was telling natural science, natural philosophy, natural science, natural philosophy. I asked him, tell me, what is natural science and what is natural philosophy? He told me, solid state physics is a natural science, and cosmology is natural philosophy. I told him, guy, you were not upgraded in your Jesuit community, because cosmology became natural science in 1990. What it was before? Let's go, of course, to the ancient Greeks. Here is some quote from the poetry of La Fontaine, and it was, of course, about one of the main heroes in ancient Greek philosophy, Democritus. They say that our fellow citizen has lost his mind. Reading has ruined Democritus. If he knew less, he would have more sympathy from us. There are more worlds, he claimed, in number infinite, and each of them may have in it another Democritus. Okay, something would remind me the front page of New York Times recently, when there was discussion about multiverses, and four of my good friends became the hero of this newspaper. You can read it, by the way. You just write New York Times, and the title of the paper, Cosmic Brains, Have Cosmologists Lost Their Own Brains? Question mark. Okay, when I told to one of my friends that, guy, you have really to bring this guy in the court, because it's insulting. He told me, Slava, you don't understand how the system in America works. I already thanked him for this paper, because in America the main thing is publicity. You see, on that you make money. Now, what about universe? You know that actually Francois Englert told me the story from Kabbalah. He doesn't understand too much in Hebrew, but he asked to translate it to him. And the story was how God created universe. The story sounds like this one. God was bored at some point, and he decided to create something nice. But God was everywhere, so he had no place where to create something. But because God smart, he shrinked to the point, produced outside universe, expanded, and found himself in very boring universe, because it was the most possible symmetric universe. In Kabbalah, it's not specified. It was de Sitter, Minkowski, or anti-de Sitter. But now we know that there could be only these three possibilities. Then God was thinking a little bit, shrink himself back to the point, but before shrinking, he distributed a little bit garbage around without smell, and this garbage is called quantum fluctuations. You see, because it has no energy to smell, expanded, and these quantum fluctuations spoil the perfect symmetry, and we got evolving nice universe. You see, and this thing is expressed in Kabbalah in the following way. Only by their breaking could the divine configuration be perfected. For those people who are interested, I give the full reference here. You see, so it was not blah, blah, blah. Because Francois was using for spontaneous breaking of symmetry. I thought, come on, it's triviality, let me use it better. But he also could use it. Yeah, now, then, of course, you know, you can look the history of cosmology. Indian was thinking about this Hindu cosmology, about cyclic universe. They even, by the way, estimated the age of the universe about correctly, like one Brahma day, or about few billion years. You see? Then Aristotle tried to measure the size of the universe, and he found that the size of the universe is about a couple of light years. Made a big mistake, as you know very well. But it was all at the level of blah, blah, blah. But facts are the following, that everybody knows that there exist stars, and in between the stars at the beginning of 1920, so it's just 100 years ago, people have seen some nebulae. They were in the so-called Messier catalog, which I think counted about 134 nebulae. And nobody knew what is this. They are within our Milky Way or outside of our Milky Way. Is it separate galaxies or is just globular clusters? Some happen to be globular clusters, some happen to be separate worlds, as Kant was calling them, or separate galaxies. Okay, but Kant was speaking about this nebula as different worlds. Now, okay, only 1921, this is Hubble, okay, some people also give credit to one of his assistants, was making observations on this telescope, 100 inches telescope, it was 21, and he managed to identify separate stars in Andromeda, Cepheids. And he was able to prove in such a way that Andromeda is outside of our Milky Way. Of course, today nobody speaks about one galaxy, etc. There is nice pictures, okay, of different galaxies obtained by Hubble telescope here. You know that, okay, how you can memorize very easily what is the number of the stars in typical galaxy. This part of my talk loves some billionaires, you see, whom I met in Canada recently, because I tell that, okay, every galaxy has about 100 billion stars, and then within observable horizon there is 100 billion galaxies. And the total mass there in all the galaxies, 1055 grams. In fact, actually, I was amazed because Friedman, when he was writing his paper, people called him mathematician. I do not know actually up to what extent he was mathematician. The guy was even experimentalist. He was working in meteorology and moreover making experiment, throwing the bombs from the helicopter, not helicopter, from the plane to know when one has to throw these bombs, you see? So, and he had actually a very interesting history because at the beginning just Einstein ignored his paper. He said, oh, this guy made mistake. Then Ehrenfest explained Einstein that Friedman didn't make mistake. Einstein wrote apologies. You see, but at the beginning Einstein introduced cosmological constant because everybody was preoccupied with the idea that universe should be eternal and static. And stars should be eternal. This was the question why, okay, we do not have infinitely bright sky because it was so-called Olber's paradox, as you know very well, you see. But then Friedman got expanding solution. Einstein introduced cosmological constant just to get static solution because, as you know, matter is always attractive. But cosmological constant, or what people call now dark energy, is repulsive thing, okay? So it's anti-gravity. So if you want to compensate attraction by repulsion, you have to introduce cosmological constant. After that, Einstein called that it was his greatest mistake in life. But, okay, again, he was perhaps not right. In this particular case, even Einstein was not always right, as you know, always right. I do not know who is. So people who are doing nothing. Okay, so now, then cosmology, of course, Landau was prohibiting to use even mentioning about cosmological constant, I can tell you. But then Hubble was able also to measure the spectral lines of the certain elements. And finally, he statistically established that the other galaxy far away are escaping from us. And it was interpreted, the spectral lines were redshifted as a Doppler shift, of course. No, okay, because it was a popular lecture. Now, no sound, perhaps. No sound, but okay, doesn't matter. You all should know what is Doppler shift. Yeah. You see, I have to decide between myself and speed of sound. Yeah, so you can always hear this thing in the track. Then, after that, Hubble interpreted what he introduced, this kind of spectral shift, telling that the recession velocity for each galaxy is proportional to the distance to the galaxy, so-called Hubble law. And h is called Hubble constant. Although, of course, it's not constant, it's changing with time. But today, it would change by factor 2 during the period of time, 13.7 billion years. So on our lifetime scales, it's really constant, you see. Now, if you take two nearby galaxies and then divide distance by velocity, you will get the estimate of the age of the universe, because all galaxies were together, roughly speaking. So universe was produced as a result of what people were calling Big Bang. And in fact, actually, in relation with these things, there is another nice story, because Zelmanov in 1937 wrote first paper about expanding universe and published in Soviet Union in the journal, Astronomical Journal. But second part of the paper was not published, and it was published with 16 years delay. Only in 1953. You know why 1953 was a remarkable year in Soviet Union? Because Stalin was gone. And by the way, this week when Stalin was gone, as I found in some newspapers, in Moscow, people were showing Romanian movie with a nice title, The Dream is Realized. It was about some guy from Romania who became the member of Kolkhoz or something like this one. So can you imagine the people were running and trying to remove all this advertisement about this movie? But, of course, when Zelmanov published his paper about expanding universe, and that the universe had a finite time, that Marxist-Leninist Russian philosophers decided that no, it's in contradiction with Marxism-Leninist philosophy. And 13 billion years is not enough to build communism, perhaps. Therefore, everything was prohibited there. By the way, okay, these guys were going also to attack physics furiously. But physics in Soviet Union was saved, of course, by nuclear bomb. Now, I'm not very sure that was a very good idea to save physics there, but nevertheless, it's a matter of fact. And in fact, actually, when Zeldovich escaped after making nuclear bomb, he did his practical contribution. Also, he invented, by the way, all this Katyusha, what is known like Grad right now. Yeah. He decided to move as far from this kind of shitty activity as possible. Therefore, he became cosmologist and astrophysicist, you see? Now, okay, what we knew also after 1920, besides that universe is expanded, we knew that there is baryonic matter, about 25% of helium The rest is hydrogen. Then there is a little bit deuterium, and all of us are in the trace amount, really negligible amount. But nevertheless, because we know the binding energy of the helium-4 is 28 mega electron volt, it's released when you form helium atom, you could estimate what would be the brightness of the stars if you wanted to produce all helium in the stars. And then you would get that our sky should be 100 times brighter than it is. This is the reason why Gamow in 1949 came to the idea of nuclear synthesis in the early universe. You see, when universe was hot, as he said, moreover, he had two collaborators, Alpher and Hermann, and you know, they calculated something. Of course, they could not calculate with this kind of accuracy the temperature of this primordial radiation today, but it was some kind of accident, because you know that his guys, they didn't know even the freeze-out concentration of the neutrons, because freeze-out concentration of the neutrons for the first time was calculated correctly by Hayashi. It was published in some Japanese journal, which was translated only in 1970 in English, you see. So, but these two guys nevertheless told him that the temperature should be about 10 degrees or 5 degrees. Then Gamow was giving an interview to BBC. He forgot this number. He told it should be 3 degrees. In fact, it's 2.7. This was the reason why in some of the popular papers I wrote that it looks like these Russians, like Friedman, who was estimating the age of the universe, taking the total mass of the universe, 1055 grams. And Gamow, who estimated this temperature like 3 degrees, I wrote in some paper that it looks like some Russians had direct telephone line with God. But then Weinberg was upset with me. He told that Alpher and Hermann were not Russian. I told, come on, okay? They were also Russian Jew who emigrated to America. Yeah, so nevertheless, okay, it was the only thing which is known. Also, there was Zwicky, who was analyzing the dynamics of the clusters of galaxies, and he came to the conclusion that there should be dark matter in the universe. You see, but nobody was taking this thing seriously. Then about large-scale structure of the universe, clusters of galaxies or superclusters, filaments, voids, nothing was known. 1980, when I was spending so-called time on 6-meter Russian telescope in Zelenchuk, I asked why they needed to put 6 meters, the largest telescope at this time, okay, in this kind of very bad place concerning weather, why they didn't do it in Armenia. Okay, I was told that condition was that it should be in Russian federations. It looked like this guy already knew that everything will decay, you see. That was also very close to the place where all these big party bosses had their so-called dachas, so vacation houses. So nothing was known. Then the next piece of information came from these two guys, Penzias and Wilson, in 1965. Because they used this radio antenna, but they could not remove unavoidable noise, irrespectively in which direction they were pointed it out, okay, which had effective temperature about 3 degrees. But of course, they were able to measure only a few points on this curve, which is called Planckian curve. You see, therefore it was just assumption that it's remnant of primordial radiation. They could not go to the higher frequency because of the atmosphere. There was not known windows in the atmosphere at this point. It was plausible hypothesis. They had no idea what is this, and then some guy from Princeton who came there tells them what is this, because in Princeton at the same time, Dicke and company were preparing experiment with, in fact, purpose to find this radiation. First attempt, they could do it in 1940 already. But, of course, there was no absolute proof that this is the remnant of the so-called Big Bang. Because I still recall a lot of papers written by Martin Rees, who tried to produce all this radiation at redshift about 1,000 and then trying to thermalize it, etc., because spectrum was not measured very well. So it was, in fact, 1.5 fact about universe and nothing else. This was the time when I came to cosmology, and the books people were writing on cosmology were like this one. Because less you know, longer is book. You have to describe all possibilities. And if you take Zeldovich-Novikov book, okay, Structure of the Universe, which was written in 1973, it had 800 pages, and most of the material now there is completely irrelevant just, you see. Also, by the way, people tried to build telescope to try to find, because what these guys have seen, they have seen the same temperature in all directions on the sky. And if one believes in the theory, then this should be the picture of our universe when it was 300,000 years old. And you do not see any variation of the temperature, so you do not see the seeds from which galaxy can originate. You see? And you understand that one of the differences between non-expanding and expanding universe is that in non-expanding universe, gravitational instability is exponentially fast. But in expanding universe, it's very slow. It's proportional to the size of the universe. So universe expanded by factor 1,000, the inhomogeneities has grown by factor 1,000. Therefore, there should be something here. This was the main question, yeah? So now, but nevertheless, if we would assume that all these kind of hypotheses are right about primordial origin of the radiation, etc., then what kind of thing we would get? We would get the theory of so-called hot expanding universe. You know, because if you take the quanta in the box, then when the box is growing, then the quanta is size, I mean the wavelength is growing also. So it means that the temperature, which is inversely proportional to the wavelength of the quanta, is decreasing inversely proportional to the size of the universe. And if today the temperature is 2.7 degrees, then when universe was 1,000 times smaller, the temperature was about 3,000 degrees. And why 3,000 degrees is so great number? Because it's the temperature of ionization of neutral hydrogen. You see? In fact, actually, the energy of ionization of the hydrogen, particular energy, is 158,000 degrees. But because there are about 10 billion quanta per each atom, and plus there is so-called entropy factor. When you calculate cross-section, the number which you get for the full ionization, according to Saha formula, is just 3,000 degrees. And then you know that before this moment of time, okay, all hydrogen was ionized. Why it's so important? Because cross-section on the free electron is much larger than cross-section of scattering on the hydrogen, neutral hydrogen. Because free electron, photon comes and can move very easily. But if it's neutral hydrogen, then photon which is coming should move electron together with its nuclei, you see? And this is the reason why Thomson cross-section is 10 minus 24 centimeters squared. And after this moment of recombination, these primordial quanta should come to us practically without scattering. And it's the moment of time which is about 300,000 years. Moreover, this kind of recombination doesn't happen instantaneously. The process is a gradual. It happens during 90,000 years. If, for instance, if it would be instantaneous, then the CMB fluctuation, about which I will speak later, would never be polarized. You see, polarization is measured. Now, then, when you go a little bit before, to the moment of time, 3 minutes after Big Bang, this is, by the way, the reason why Weinberg called the book's first 3 minutes, yeah? Because he was concentrating mostly on nucleosynthesis. Nucleosynthesis in this kind of expanding hot universe was fully calculated by the guys who were working also on American nuclear bomb, by Wagner and company. They went up to the element, I do not know which element, but of course they found the deuterium abundance, everything, you see? And it was amazing thing. Of course, they also found that the amount of helium is 25%. And the most amazing thing is that you see why, for instance, it's 25%. If helium would be formed immediately after neutrons would chemically disconnected from the protons, okay, would be no conversion, the amount of helium would be 32%. But you know that, okay, it didn't happen because concentration of deuterium was not high enough, and you needed to wait when it will grow. And, okay, you needed to wait about 200 seconds. And what is the lifetime of neutron? Is precisely 900, about 900 seconds. So 1/4 of all neutrons disappeared because they decayed. Free neutrons decay. Only neutrons which are captured in nuclei become stable, but free neutrons doesn't live very long, you see? And as a result, you are getting 24%. Moreover, the most sensitive indicator to the whole thing also from this nucleosynthesis is the amount of deuterium. It was very difficult to measure primordial deuterium, but deuterium tells you what is the percentage of baryons you could have in the total universe. And now deuterium is measured by Max Pettini in the clouds. It's very difficult measurement, which are at redshift about 3.5 with unbelievable accuracy. And using this deuterium, you could predict what is the density of baryons in our universe today. And this result comes in full agreement with CMB measurement, and this nucleosynthesis has nothing to do with this measurement. You see? I think it's a very convincing thing. Now, concerning recombination, this 90 degrees or 90,000 years, the rate of recombination of hydrogen, neutral hydrogen, is mostly comes from very rare process. 2s to 1s hydrogen atom decay. It cannot go directly, if you still remember school physics, yeah? Why? Because you have to conserve momenta, and you have to produce at least 2 photons. Very rare event, which is 100 million times more rare than the transition from 2p state to 1s state. You see? But you could ask, but why not through 2p? You could have this recombination. Because as a result of the transition from 2p to 1s state, you form so-called Lyman alpha quanta, which has resonance cross-section of the absorption on the neutral hydrogen, which is million times larger than 10 million times larger than the cross-section of the scattering of the free electron. You see, now, therefore, this ray event play very important role at the moment when universe becomes transparent. Now, from experimental data, how do you think with which accuracy you could measure the decay rate from 2s to 1s state? Yeah, from cosmological data. Just with which accuracy you could measure the probability of this very rare event. 5%. You could ask question, but how it's comparable with the lab measurement? I can tell you cosmological measurement much, much better than the lab measurement, because in the lab accuracy is plus minus 100%. People have seen this kind of event, but there is not enough statistic to measure the rate. You see, when I asked Hensch, who is specialized in 2s state, he told me, oh, I need actually a device which is 10 times larger if I want to measure this thing. So you see, cosmology became even competitor of particle physics. Not particle, atomic physics. Come on, particle physics. Particle physics, there is not so much about particle physics. So when I came in cosmology, you see this gentleman who is sitting like this one and see this sky. He is a little bit upset because he doesn't understand how you could form him if universe, when it was 300,000 years, was so homogeneous and isotropic, because, okay, the same color means that there is no little variation of the density even. Because as I told you, there is no exponential instability here. Before that, universe is very homogeneous. Of course, if there would be smaller homogeneities, then these smaller homogeneities could grow. You see, here is the principle which works. Richer becomes even richer, especially on stock market, you see. So, it's the principle of gravitational instability. And then people can calculate, starting with some kind of initial condition, it's so-called millennium simulation, everything is computer, and then they are getting, starting from small inhomogeneities, this kind of complicated structure of the universe, where you have clusters of galaxies which are connected by filaments. Filaments are connected by walls, and in between walls you have big voids, and this is called web structure of the universe, you see. But the question was that from where all these perturbations are coming and why they are not there. Of course, why they are not there, you could explain that your equipment is not sensitive enough, right? And nobody could make any estimate because there was too many uncertainty parameters. But nevertheless, it's clear that real universe should look like this one when you observe it. And when, okay, I wanted to do my PhD, at the beginning I was astrophysicist, therefore, okay, I found that it's too much for me. Very boring and a lot of mess, yeah? Therefore, okay, Chibisov told me, let's calculate it, like they originated from quantum fluctuations. And then we wrote some paper, and then we discovered that we have to refer the moment of origination of these fluctuations to the moment which is 10 minus 36 seconds after Big Bang. I will explain you how, after that, we can be sure that what was calculated at this moment of time is reliable irrespective of any particle physics. And you know who saved us here? So-called causality principle. After these guys, so-called seeds for the galaxies were produced, they were outside of any causal contact. Therefore, nothing could happen with them. They were produced, as we discovered, during the so-called inflationary stage. What is quantum fluctuations? Okay, if you ask question, what would you prefer, your iPhone or to be alive? I'm not very sure what answer I would get, because now people cannot imagine life, good life, without iPhones. But the question is how to have simultaneously both. And of course, when God was distributing this garbage, which is called quantum fluctuation, he found the way, quantum mechanics. Why? Because why iPhone are functioning? Because when an electron is moving around center, it emits electromagnetic waves. But of course, if it will be emitting electromagnetic waves, then in Maxwell's theory, it should end up in the center, and therefore matter will be unstable. But unless there is no this uncertainty relation, you see, because when now electrons try to get inside, then it acquires huge speed and gets outside of the nuclei, and it's called completely stable state for the atom, which is the ground state of the atom. iPhone functioning because of the higher orbit, and we alive because the ground state is stable. You see, and then we wanted to use these quantum fluctuations, okay, which were, okay, it shows here, which are unavoidable because of the uncertainty relation. Here, the guy on the left, you can guess that it's Heisenberg. But quantum fluctuations in the density distributions are large only in extremely small scale, 10 minus 33 centimeter. But they are very, very small on galactic scales. Okay, 50 orders of magnitude smaller than we need for producing galaxies, because we need 10 minus 5 instead of 10 minus 58. And at the beginning, okay, I saw that I failed with my PhD because I do not know how to make it. Okay, you of course can make formulas, can make everything, but when you get negligible number, you do not know. But then actually we realized with Chibisov that there could be some way. Today we see dark energy. You ask question, why do we need dark energy? Today, okay, dark energy is useless for all practical purposes. Not for scientists, but for life. Because scientists could write infinite number of papers, increase citation index, and make good salary, or reasonable salary, okay? So, but for life it's completely useless, and the only explanation which I have, okay, perhaps will sound too philosophical. God decided to give us indication that there can be this kind of state of the matter which can be extremely useful in the past. You see? Okay. And now, imagine universe. Now, can I make, okay, I will make sound. Wait. Okay. So here is the universe, how it was understood before. Here is the speed of the expansion, here is the time. And you know that gravity is attractive force. Therefore, there should be some infinitely large speed given to the universe. And then the only role of the gravity is to decelerate this expansion. Now, imagine now car, okay? And this is speedometer, yeah? So, wait 1 minute. So you could ask the question, who put car in this kind of bloody state, yeah? For 300 kilometers per hour. And you know that it could not come from somewhere in nowhere. The same question appears about universe. And you know what happens with the car? First of all, you have to accelerate it to speed 300 kilometers. And therefore, okay, the more natural picture for the universe would be like this one. Remove this kind of stage and substitute the stage of exponential expansion where you start with 0 velocities and then, okay, reach maximal velocities, and finally, if you are not committing suicide, you put your leg on the, how it's called, bremsen, yeah, on the, yes, breaks. Then you are getting much more logical picture. You see, picture is complete. Therefore, to imagine something else is impossible. But how can you make this kind of accelerated expansion? What plays the role of gasoline for the producing of our universe? Of course, what people call dark energy. Today, it's useless. Today, it's useless, but in past, it was very useful. Why? Because using this kind of stage, you can extract infinite amount of energy from the gravity. You can start with nothing, and you know why? Okay, you were speaking about energy conservation law. Of course, energy conservation law in a certain sense always works, but you see, if you will take ball with density rho and radius r, then what is the gravitational field which you will see far away from here? Okay, so gravitational potential will be of the order of mass, so rho r cube divided by this small r distance. But what I forgot here in Newtonian theory, I forgot to write the term like minus m squared divided by r. Negative gravitational energy of self-interaction. So write it. Rho g rho r cube squared divided by r. And you see, I increase rho within the given radius, or I increase the radius. Finally, I can compensate these two terms. I can get 0. This is the explanation why the energy which you need for producing universe is 0. You can produce universe out of nothing, because total energy of these galaxies is fully compensated by the gravitational energy of self-interaction. You see? This is the reason why universes could go like this one. I recall that Zeldovich was standing, giving lecture, and then, because this kind of cosmic inflation appears, and he said, but why we cannot produce universe in Minkowski space, yeah? You make fluctuation, normally quantum fluctuation. If it's filled not by dark energy, but by normal matter, then this quantum fluctuation of the scale 10 minus 33 centimeter cube will immediately recollapse. But if you put here the matter in the state pressure is approximately equal minus energy density, which is in fact cosmological constant or dark energy, then instead of recollapsing, it starts to expand like crazy, you see? And then within 70, cosmological 70 Planckian time, you are making within this universe the amount of matter which is 10 in power 80 grams, you see? It's, after that, of course, there is redshift, and then the total amount goes down to 1055 grams, as we see today. So now, when we use this stage, we finally were able to resolve the problem with Chebyshev. It was 1981. And we got the theory, okay, in this paper, because actually Americans for a long time tried to ignore it, of course, as usually. But I forgot where is one more page, but doesn't matter. Okay, it was published already in 1981, but okay, it was written in 1980. Okay, forget about this bloody priority. You know that actually it reminds me. So, but in this paper we made 4 unbeatable predictions. First prediction was that universe today should be flat. So it should have today, at present moment of time, the geometry, which is Euclidean geometry. So sum of the triangles sum of the angles in the triangles made out of 3 galaxies should be 180 degrees. You told that everybody believed in it. Come on, if you would tell astronomer in 1980s that our universe is flat, he would send you to psychiatrists, because in all the galaxies, people could not count more than just few percent of the matter needed to make universe flat, you see? Because as we know, 4% in total. Then people were guessing about dark matter, but even with dark matter, okay, which people were normally putting in the form of the dark stars or dark planets, people could never get anything besides of 20% of needed matter to make universe flat. 1993, okay, there were observations of this kind of dynamics of the cluster, and people were publishing robustly that it's only 30% of matter which is needed enough. It's only 30%, okay, and 70% of the matter is missing to make universe to have flat geometry. You see? 1993, this was the reason why, for instance, some of my friends started to write papers how to make universe, okay, which is open universe. But the favorite model was this model with negative curvature. You see? I remember that when Wheeler came in 1980, I thought that he is crazy because he was speaking about closed universe. And okay, nobody from realistic people would ever think that it has zero curvature, which is expressed in terms of so-called cosmological parameter omega equal 1. Doesn't matter, I'm not going to define it. It's actually the ratio of potential energy to kinetic energy. It should be equal to 1 to have flat universe. Now, second prediction was that perturbation should be adiabatic. What does it mean, this thing? Okay, you can have two completely equal boxes in the universe, right? The same size. But, for instance, the number of photons in one box can be 100 photons. It's as an example. But in the other box, it can be only 98 photons. So you admit variation of the energy density. But you know that the number of photons per one baryon should be staying constant. So you predict that there should be in the second box 49 baryons. If you would find 47, the theory is ruled out. The first way to rule out, to measure and find omega non-equal 1. The second way to find that the number of photons and number of baryons are varying in a different way. Moreover, you know what was the most popular theory in 1980, which people were claiming in agreement with everything? You should know. Because you were referring to Peebles. Of course, everybody always follows what Princeton people say. And it was the theory where baryons were distributed at the beginning homogeneously, but photons perfectly homogeneously. Therefore, it was called the entropy theory of the perturbations, initial perturbations. Adiabatic perturbation nobody was considering because it was, besides of Soviet Union, because Zeldovich knew how much this data cost. He participated in the building of Russian nuclear bomb, which was exact copy of American. And by the way, who has stolen everything from American? You have seen the movie Oppenheimer. I haven't seen it, but you have seen it. Huh? Fuchs, yeah. And in America, he would deserve electric chair. But in England, he got just 20 years in prison, and he was released after 10 years. He passed, by the way, all information to KGB. Then, from this KGB, people were showing the document only to Kurchatov. Kurchatov was coming and telling people what they have to do. But Russia knew, by the way, that also it's not very reliable bomb. Therefore, there is 10% probability that it will not explode. Therefore, they wanted to improve it. But they got order, no, first you explode exact copy, and after that you do whatever you want. So therefore, there was 10% of probability they will lose their life, because the other team already was prepared. In the first team, 99% of people who were working on nuclear bomb were Jews. In the other team, there was no single Jew. But fortunately, it's exploded for these guys. Therefore, Zildovich knew how reliable are astrophysical data. Therefore, he was continuing to push this adiabatic theory without paying any attention to what people in Princeton say. But Peebles was still captured to this entropy perturbation. I remember in 1997 we had exchange with him because, okay, we wrote some joke paper with Linde, but Peebles was very happy with it because he was telling, we were solving some, from my point of view, some theoretical question which has nothing to do with reality, but people, oh, okay, it's an agreement with the galaxy formation. Of course, after first data, then if you remember that there was competitors, so-called, not Mont, more serious competitors to the theory of adiabatic perturbations and to this kind of quantum fluctuations were cosmic strings, plus then Turok invented so-called textures. I do not know what is this, but he was going and convincing everybody that these textures working perfectly. I recall that Ginsburg asked me to give talk about this paper in Physref letters. I remember that I come, going to speak about these textures, Ginsburg told me, Slava, what kind of bullshit you are talking here? I told him, Vitaly, you asked me to do it, yeah? I wanted to know how to translate the word texture in Russian. When I said him textura, he was disappointed and he thought, but here I think we have to stop. You see, but of course, all these things disappeared. But cosmic strings were existing for a very long time, and by the way, also I lost a bottle of vodka to Brandenberg, who doesn't drink at all. And criteria was that I told that in 5 years, in 3 years, nobody will be working in this field besides of you. And then some guy from Ohio State published paper in the wrong moment of time. So what can I do? I can admit. Also, when they appeared dark energy, I had bet with Vilenkin that it will decay in half a year. Because supernova, come on, no serious people believed in this supernova result. But I lost, fortunately, bet. So then the prediction is perturbations are Gaussian. So you see this lady, I do not know who is she, and therefore I didn't ask permission to get her photograph. Therefore, please hide this slide if you are going to release the talk. You know, where's the whole image? It's not in intensity, because you can change intensity, but you see the same girl. The whole image is in phases, you see, of the image. And if you start to destroy phases a little bit, then you know that, okay, at some point you will not recognize the whole thing. So what is the most democratic is the Gaussian distribution of these phases. You see, so then everybody is equal to everybody, of course somebody, but some are more equal than the other. Okay, so therefore prediction was that this gravitational potential is Gaussian random field. The most democratic thing, you say Gaussian, you know everything, because all high-order correlation functions are expressive. When you say non-Gaussian, it means nothing, because there are billions of the version of non-Gaussian, billions of billions, you see? But Gaussian means unambiguous. So the prediction was that this gravitational potential should be Gaussian random field with admixture of non-Gaussianities at the level, if it's 10 minus 5, with admixture of non-Gaussianities at the level 10 minus 10, because F and L prediction was that it should be equal to 1. Why it appears at all? Because of nonlinearity of Einstein equations. When we are doing quantum fluctuations, we take given background, which is considered non-perturbatively, and make small perturbation theory. But of course, there are high order corrections, and this high order correction induced in the Gaussian field, okay, the non-Gaussianities at the level which is 10,000, 100,000 times smaller than the amplitude of the gravitational potential itself. You see? This is an unavoidable thing. This FNL of the order of 1 is nonlinearity of Einstein stuff. So, I think very robust prediction, because if you would find non-Gaussianity, this FNL, at the level like 100 or 300, then the theory is killed, ruled out. I will discuss in the next lecture how you can screw the theory to explain everything. But the theory which explains everything explains in reality nothing, as you know very well. Okay? Theory should have robust prediction. Now it's already 3 robust predictions. Smoking guns, non-confirming any of them, would just kill the whole hypothesis. It's predictions, okay? They were not measured at this time. And the last thing, which was the most non-trivial, okay, the prediction of this picture, which was characterized by some number 0.96. You see, it's not 0, it's not 1. You ask me how 0.96 appeared. Okay, without going to too deep explanation, I will tell you the idea. Oh, by the way, the ratio of female to male also accidentally at birth is 0.96. Do you have any idea why it's so? No, besides that, men, of course, should fight for the homeland, yeah? And therefore they disappear. But finally, actually, this ratio becomes, it's also without, this number is without so-called systematics, which is introduced in some countries, as you know, as you can suspect. You see, so it's average over the countries, which I'm not making artificial. But what does it mean, this 0.96? Because gravitation potential squared behave like logarithm of the scale to the typical scale of CMB. But because you are measuring the things within small interval, you could approximate this logarithm in galactic scale as a scale in power 1 minus ns. So it means very simple thing that, okay, that the amplitude of perturbations should slowly grow towards to the larger scale, which is unexpectedly. And the theoretical number, which comes here, 0.96, is like 1 minus 2 divided by logarithm of galactic scale to the typical scale of CMB. So it's megaparsec scale divided by millimeter scale. And logarithm is precisely equal 50. So you are getting robust predictions that spectral index should be smaller than unity. And this is the only formula in the whole physics which was experimentally confirmed and which simultaneously includes gravitational constant and Planck constant. You see, there is other formula like Hawking radiation, but Hawking radiation was never found. It also involves Planck constant and gravitation constant. But this 0.96 also is the formula which involves quantum plus gravity. Now, and I remember that we had some Nobel symposium in 2003. Okay, there was a lot of string theory, etc., 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 but there was also experimentalist from CMB. And Lyman Page, he was one of two principal investigators on this WMAP project, yeah. And then people were voting. What is more important experimentally? To find deviation of omega from omega equal 1, or to find this spectral index? Of course, Lenin Susskind was telling deviation from omega equal 1 because I have some string theory with a tunneling in landscape among 10 in power 500 vacuum where, okay, I can predict that deviation should be few percent, yeah? But you understand that most, of course, voted for this omega equal 1, but I said it was stupid. It's the same story as to invest money to CP violation or CPT. Okay, looking for CPT violation, which is there. There is no violation. And then in 2003, okay, Lyman Page, who was there, also wrote to me, we are writing a proposal to get money to do our small angular scale CMB experiment. It's in Atacama. If I say that simple models of inflation, in fact, it's the only inflation require 0.95 plus minus 0.03, is it correct? I'm especially interested in the error, specifically if NS is 0.91, would you throw in the toil on inflation? I wrote to him, okay, that if you will find 0.99 plus minus 0.1 as well as 3 sigma, no problem. Because before that, I asked Lyman how much he can, after he found this deviation, I asked him how much he is ready to bet on these deviations, which he has seen as the first guy. He wrote to me a lot of thousand, I thought not from grant money, from personal money. He wrote me a lot of thousand plus infinite amount of beer. Okay. So now, for robust predictions, okay, which were done just making simple assumptions that universe at the earliest stage went through the stage of accelerated expansion, which amplified the quantum fluctuations. After the end of accelerated expansion, you produce the seed for the galaxies. But then these seeds for the galaxies, they are sleeping because of causality principle. Because the causally connected scale is huge only on inflation. But after the end of cosmic inflation, the size of causally connected scale is 1 divided by Hubble constant, so it's time. And then for 300,000 years, these kind of embryons for the galaxies were sleeping. And when they entered inside of causally connected region, we know already all physics. They woke up and started to evolve. You see, and then you could see the things in the CMB observations. But now, this was the first lecture. I think if I will finish right now, it's okay. So, I'm already speaking 1.5 hours, I think.
You can speak still 5-10 minutes?
No, I don't want, I'm sorry. Yeah, so now, and then, okay, there will be some kind of semi-technical part, but I will give not 4 lectures, I will give only 3 lectures because I need to leave on Wednesday evening. No, on Thursday in the morning I have train, yeah. Yeah, okay, thank you very much. But then, okay, there will be some technical part, just for you to see some kind of formulas. Then you can close the eyes if you don't want to see them. But nevertheless, the rest will be stories about experiment, and next time also I will discuss more philosophical blah, blah, blah about multiverse. You see, because for a very long time it was in the center of discussion that inflation has trouble. Maybe you heard about it. And Paul Steinhardt was attacking the whole thing in Scientific American. Have you seen it or not? Then there was reply to Paul Steinhardt signed by 33 physicists. When they told me, okay, to write this letter, I told, come on, I never sign collective letters anymore after bad experience of life in Soviet Union, where people were executed thanks to these collective letters. And then actually, this guy, Avilov said once, when Einstein, okay, when 30 people wrote book in 1930 why Einstein is wrong about general relativity, Einstein said, okay, if I'm really wrong, one would be enough. Why you need 30? You see? Okay, good. So here I finish.
Thank you very much, Slav, for this great lecture on the genesis. So it is a very important paper, 1981, with the calculation of the relation between anisotropies in CMB and quantum fluctuation. Was a history of physics, part of history of physics, a paper by Slav. Now we have time, plenty of time for questions.
You don't need to be politically correct. And you don't need to hesitate to ask stupid questions.
I have a stupid question.
Very good.
And the other side, that is the comparison between the observed distribution of matter in the universe and the CMB anisotropies. You can say something
It's in perfect agreement with everything, because actually the only thing where you can still believe a theory, where you are in linear regime. For instance, if you will take this baryon acoustic oscillation, recent DESI result, yeah, then it's just in perfect agreement with everything what is following from CMB. People try to make sensation out of everything, but you should not forget that you have physics and astrophysics. Okay, I ask auditory, who knows what is the difference between physics and astrophysics?
Physics is more general.
No. It's actually, what do you mean more general? Of course, physics is more general, but doesn't include astrophysics, in my understanding.
Astrophysics is about physics on big scale.
No, it's also not the case, because my definition, no, again, good example, but nevertheless, my definition is different, yeah? Because when systematics come under control, then it becomes physics. You can forget about the word astro. It means that you are sure what you see, really. You see? And astro means very uncertain thing, especially when it goes about scales where there is no linear structure. You see, when you have some troubles with no linear structure, I am sorry, it's not my problem. It's the problem of those people who are doing all these numerical simulations. If, for instance, you cannot derive your existence solving Schrödinger equation for hydrogen atom, yeah, it doesn't mean that Schrödinger equation is wrong. Correct? Correct. So if you cannot explain very complicated biological phenomena starting from elementary structures, it doesn't mean that actually the fundamental theory of elementary structures is wrong. It means that you are missing something on your way. A good friend of mine was telling Batalin, yeah, that God gave us few exact solutions, and our job as a theorist is to develop perturbation theory around them. This is everything what we can do. You see, when the thing go to nonlinear physics, the things, first of all, goes out of the control. It's not anymore theoretical physics. And then you are using computers, maybe it's very useful sometimes. Sometimes, for instance, like with this astronomical object, it can be useless, but one should not make too big sensation. It has nothing to do with each other. For instance, supernova. It's so complicated physics, okay? And therefore, when some people come and tell me that they made precision measurement from supernova, is a joke. You see, these guys just do not know what does it mean real measurement. Real measurement means that when statistic dominates over systematics. Only in this case you can use criteria of sigma. For instance, in particle physics, even in particle physics, actually, it's a complicated thing because LHC is not very good device. It's very dirty device because you are colliding two bugs with a lot of quarks and then you are getting a very messy picture. This is the reason why, for instance, I would prefer if people would make in Japan, because they were considered 3 projects, linear accelerator to the energies up to 300 GeV, like Higgs fabric, yeah? Or this light bird to measure B mode of polarization. But this B mode of polarization I will discuss when I speak about experimental verifications, you see? Okay, because there was actually, you know what was in 2014? There was 2 disasters, not just occupation of Crimea, but also there was bicep experiment, which was the other disaster.